Welcome back to the course on measurement and instrumentation, and this is the fourth week of this course and we are discussing about analog meters. This is the second module and we are discussing the 11th lecture of this particular module. In the previous classes, in fact, we have seen different ways to classify the analog meters, as well as we also saw certain kind of electrical measurement tools like ammeters, voltmeters, ohm meters, so on. Okay. So, we have seen that there are a variety of instrument based on what principle it utilizes and how the pointer move, what kind of principle is used for having this kind of deflection, or what we use for controlling, or what we use for damping. Okay. So, based on all these parameters, we have seen that there are variety of instruments or analog tools available. Some of them are like permanent magnet moving coil, or PMMC. We also called it moving coil kind of instrument. So, second is moving iron electrodynamometer, then induction type, electrostatic type, thermal, in which we have seen hot wire, which is very important kind of instrument, then Hall effect type, and so on. Okay. So, a number of devices or analog tools we have seen, and all of them can be, or some of them can be used as voltmeter as well as ammeter. Some of them can only be used as a voltmeter, or some of them can only be used as ammeter, and some are universal tools. We have also seen that in the classification of the analog meters. Okay. So, what we will do is, in this particular week, we will start our discussion on all of these instruments. Okay. So, if you have studied the galvanometer in the previous classes, okay, it will be very easy to connect with this particular kind of tool because the torque equation and other things are very similar to that. Okay. So, let us start our discussion on PMMC instruments. Okay. These PMMC instruments have very high accuracy and sensitivity, and that is why they are suitable for precise DC measurement. And please note that when I say DC measurement, I am actually covering both current as well as voltage. So, you can make a PMMC instrument suitable for detection of DC current as well as for detection of DC voltage very accurately. Okay. These instruments have a uniform scale because deflection in these cases are directly proportional to the current which is causing this deflection. Okay. So, we will see that most of the, in all these PMMC cases, or across say PMMC based ammeter or voltmeter, the scale is mostly linear. Okay. The power consumption in these devices are very low, and only a small current is drawn to produce even a full scale. Okay. They have a very good damping approach. So, they basically exhibit excellent damping. Therefore, you have fast result. So, because the settling time is very fast, there is very less oscillation, or there is no oscillation kind of. Okay. These PMMC instruments are highly stable over the time with minimal effect of stray magnetic fields and good repeatability. So, we will see that what we can do to avoid the stray magnetic fields. Usually these are at the end of or at the edge of the poles. So, what we usually do to avoid these stray magnetic fields in case of PMMC tool. Okay. So, before we actually go to the torque equation, let us see the basic construction of a PMMC instrument. Okay. So, the basic construction of this instrument is shown over here. You can see the arrangement is very similar. You have this permanent magnets. This is another view, and this you can understand as one of similar to what we have seen in case of galvanometer. This is view 1. So, I am calling it, say, this is view 1, or you can see from the top how it looks. Okay. And this is kind of cross sectional. Okay. So, you can see this, I am calling this as view 2. All right. So, we will be using them. Okay. So, the construction is very simple. You have permanent magnet, okay, a coil, a scale. Okay, in general. Okay, we will see what are the important parts of this. We will do the anatomy of this permanent magnet moving coil instruments. Okay. So, in general, the construction is done using total 5 different important parameters or important parts. The first is moving coil, which was this. So we'll, or in this case say here, okay, moving coil. Then magnet system. This is very important, and this magnet system is a permanent magnet in this case of PMMC, okay, permanent magnet. Then you have arrangement for control, okay, or opposing torque, okay. Then you have a damping system which produces the damping torque, and then in general a pointer as well as a scale, okay. So let us learn about these components part by part, okay. The first is the moving coil in case of the PMMC tool, okay. The moving coil in this case is wound with many turns of enameled or silk covered copper wire, because usually we utilize copper wire because of its low resistivity, okay, and the enameling is done, or covering of this copper wire is done. In each turn the wires are very near to each other, and if you are not covering it, basically you are allowing them to short, okay. So now this coil is mounted on a rectangular aluminum former which is pivoted or on a jeweled bearing, okay. So you have a metal former, okay, usually this is made up of aluminum, okay. So you have, so let me redraw it, okay. So you have aluminum former, and on top of it the covered copper wire is wound. So something like this, right. So if you see these turns, I am just drawing this side, okay, a side view of this turns, okay. It will look something like this, right. And of course this gap I am drawing at very, it is very spacious while I am drawing, but it will be very close to each other, okay. So when they are very close to each other, of course there is a chance of shorting, and that's why they are covered mostly, okay. And this is coiled upon a metal former which is aluminum former, okay. And now this coil is mounted, as I have mentioned, on a rectangular former which is pivoted on a jewel bearing, okay. Now this coil moves freely in the field of permanent magnet. So you have a permanent magnet, okay, and this coil actually, so this is the top view of this former, okay, and on top this coil is, so this will move. So you have say north and south, and in this so when you have this kind of coil placed, there will be a force acting over here and a force acting over here, and because of this there will be a torque, okay. So the coil will move freely in this permanent magnetic field, okay. Now please note that the wounding of this coil is different for a voltmeter or a ammeter. So PMMC voltmeter utilizes a separate idea as well as from the PMMC based ammeters, okay. In case of voltmeters, the coil are wound on a metal frame to provide the required electromagnetic damping, okay. The metal frame is basically providing the required electromagnetic damping, or because of this eddy currents that is formed in this aluminum former, it will provide damping. However, in case of ammeter, the strategy is different, okay. In the case of ammeter, the moving coil is wound on a non-magnetic former in place of the metallic former that we have just seen, okay. So this material is mostly say bakelite or even plastic or sometime fiber, okay. So this, in case of PMMC ammeter, the moving coil is wound on a non-magnetic former. This is very important. You should always remember this, okay. The ammeter shunt effectively short circuit the coil turns, and due to this shorting effect, the eddy currents are induced in the coil itself when it moves in the magnetic field. So you do not require separate metal former for providing this eddy current or electromagnetic damping, okay. These eddy currents produces an opposite torque, and hence the required electromagnetic damping is provided by the coil itself, eliminating the need of any metal former. Now, if you forcefully provide a metal former, okay, there will be extra eddy current formed in the metal former as well as in the wire itself, okay. Because of that, there will be over damping, right? So you do not want the over damping. Of course, you also do not want under damping, but if you are using in case of ammeter or metal former, you are basically trying to do over damping, and it will of course result in power loss and other things, okay. So usually in case of this, it is avoided, okay. So this is the moving system or moving coil of a PMMC tool. The second portion of this, or second part of this PMMC construction, is the magnetic system. This is very important because your coil is turning in the magnetic field only, okay. So this magnetic field is, or magnetic system is very important, okay. So the old generation magnetic systems in this PMMC tools utilizes long U-shaped permanent magnets, okay. So something like this that we have already discussed. So this was a kind of magnetic system that was used in the older generation PMMC tools. Even currently also some of the cost effective PMMC tools utilizes this U-shaped permanent magnets, okay. Now soft iron pole pieces are attached to the magnets to shape and guide the magnetic field, okay. The development of new magnetic materials like different alloys like Elcomax or Elnico has improved permanent magnet performance, okay. And because of availability of these materials, you have actually very high coercive force, because these material possess a very high coercive forces. This, if you do not know about coercive force, you just understand this, that they will be strongly resisting the demagnetization, okay. So it will try to retain the magnetization even for longer, okay. So because of the high coercivity, shorter magnet length can be used without the loss of magnetic strength. So these materials are very good permanent magnet. They are even higher quality magnetic materials are available, but of course they require rare earth materials like neodymium, okay. So NdFeB you might have seen in case of very high cost headphones and other places, this kind of permanent magnets are used, okay. So but in case of PMMC, this Elnico is very popular, okay. Now these materials actually is allowing you to have shorter small magnets with having larger magnetic field strength, okay. So despite the reduced sizes, these materials are capable of producing very high magnetic field intensity. Particularly you are interested in this high magnetic intensity in the air gap between the magnet or the poles of the magnet and the core of the PMMC, okay. Now when you have very high magnetic field intensity in the air gap, basically this will allow you to construct a compact, lightweight and efficient magnetic system for this kind of tool, okay. So therefore the modern PMMC instrument can achieve better sensitivity, it can have better stability and uniform magnetic fields compared to the old generation U-typed or U-shaped permanent magnets, okay. In general, the PMMC instrument require a magnetic flux density, particularly in the air gap, around 0.1 to 1 Weber per meter square, and this is basically a very strong magnetic field, and this relatively strong magnetic fields enable effective interaction of the magnetic field with the moving coil, because more the interaction of the moving coil with the magnetic field, better is the torque and better is the deflection of the pointer, okay. So the deflecting torques depend on the product of a number of things we will see in the torque equation, but force we all are aware of. This force will be say B, I and L, okay. So you have the multiplication of the flux density, say number of turns also you multiply, okay, and the current, okay, and the length, right. So you have this kind of, so this length is basically in this case is the former's length, or you can say the number of turns that you have just seen, the coil's turn, okay, this particular thing, this one, okay. So this is the L I am talking about, right. So this force is from our previous studies, we know that this force in the force experienced by a current carrying conductor. Okay, so this is kind of a force that this coil is going to experience. Okay, I am multiplying this with n because this number of turns will matter a lot. Okay, so when the flux density is high, the required torque can be obtained using even a small coil. Okay, so hence the coil can be designed with a reduced number of turns, and even a smaller dimension of coil can do. Okay, now this result in a decrease in the size and volume of the instrument while maintaining adequate sensitivity and the performance of the device. Okay, so what I want to say is, this force was this, and if you multiply this say with the length, you will get the torque. So I am not going to torque right now. Let's only talk about this force that this coil is experiencing. Now I am telling you that this B is now increasing. Okay, now I have two cases. I have F1 and F2. In one case, say this is B1. In one case, this B1 is very high. Okay, now if I want to generate this F2, which is very similar to F1, and for the other system this B is very high. Okay, what I have to do is, what I can do basically is, this N can be decreased, and even I can have this L, this L can also decrease. So this L and N both are decreasing, but when this B is high, it is basically compensating. And that's what the modern permanent magnetic materials are able to provide. So very high flux density, right? So they can provide this. B becomes very high, and because of this you can still achieve the same performance that you were getting, or even better performance that you were getting with the long U-shaped permanent magnets, right? So this is in general how this construction of magnetic system affect the overall performance of the system. Okay, in PMMC instruments which are designed with a larger scale length, a greater pointer deflection is required for the same current. Okay, to obtain the necessary deflection torque, the number of turns of the moving coil can be increased, and accommodating a large number of turns basically require additional physical space around the coil, because this magnetic system, this coil is moving through this air gap, and this gap is very narrow, like 1.5 mm or so. Okay, when you are increasing the number of turns, so please note that this is coming from this, right? This is coming from this turns, right? So when you have this turns is increasing, means that what you are compromising is the space between, or the air gap between the poles and the coil. Okay, so when you are requiring a large number of turns, what you require is some additional physical space, which is of course not present. Okay, now this is achieved by increasing the length of the air gap between the pole pieces of the magnetic system. So ultimately what you have to do is, you have to increase the gap, because there is no gap earlier, because you are already covering this 1.5 mm by increasing this gap. So basically what you have to do is, you have to take this pole behind. Okay, so you have to basically play with the magnets. Okay, now this can be achieved by increasing the length of the air gap, what we have just seen, between the pole pieces of the magnetic system, and a larger air gap allows a bigger coil without mechanical interference, will still maintaining a uniform magnetic field. As a result, the instrument with long scales can provide higher resolution and better readability without compromising accuracy. Okay, so you can design a longer pointer scale or longer scale for better readability, but then it has its own disadvantages. Okay, like a fringing field occurs at the edges of magnetic pole pieces, especially near the pole tips, and this is a perfect example of fringing flux. So you see, this is for large gap, this is for intermediate gap, and this is for small gap, where you can see that the fringing flux is almost negligible. Okay, however, you can see the effect of the gap when you are decreasing the gap from large gap to intermediate gap, the fringing flux is decreasing. Okay. So, instead of remaining confined to the air gap, the magnetic flux spreads outward into the surrounding space, which appear as a fringing flux, and this spreading causes these flux lines to diverge, reducing their concentration, and as a result the magnetic flux density near the pole tips is lower than at the center of the air gap, which is totally not desired in case of PMMC tools. Okay. So, in PMMC instrument, the magnetic field near the pole tips is also no longer radial if you have this kind of consideration. If the moving coil enters this region, the deflecting torque becomes position dependent, leading to a non-linear scale and measurement errors, which is not desired. Okay. So, therefore, the PMMC designs restrict coil movement in the central region, and usually this larger gap are not preferable. Okay. Because in this central region only the field is strong, uniform and radial and this will keep your scale of the PMMC tool a linear scale. Otherwise, you may have to use non-linear scale and you may end up getting wrong results. Okay. If you talk about the actual scale, the angular span of a scale is restricted to 90 degree because of this. Okay. To obtain the longer movement of the pointer, a concentric magnet construction something like this is used. Okay. So, when you have this concentric, like you can see that this is the north pole and this is the south pole. So, you have a concentric magnetic system, and because of this you are no longer restricted to deflection, you are no longer restricting the deflection to only 90 degree, but you can go beyond 90 degree, like you can go to say 250 degree or so. Okay. So, this type of construction is used for several panel type instruments, and even you can find this in a smaller portable kind of instruments. Okay. This is a simple magnetic systems modifications that PMMC tools has gone through over the years. Okay. However, the basic U type that you have seen is what universally accepted. Okay. So, this is about the magnetic system of the PMMC tools. Okay. The third component of this PMMC tool is a control system, or which actually brings this system back to its original position. Okay. Control system we have seen in case of the galvanometer as well as in our discussion of general electromechanical indicating instrument. The same control system is utilized here. Okay. The coil is supported between the two jewel bearings. The control torque is provided by the two phosphor bronze hair springs. Okay. These springs serve to lead current in and out of the coil, and the control torque is provided by the ribbon suspension as you can see over here. Okay. Then next system is the damping system, and for damping you have special arrangements for voltmeter as well as for the ammeter. We already discussed that, but we'll just overview that very quickly. Okay. The moving coil in the case of PMMC is mounted on an aluminum former. When the former moves, it cuts the magnetic flux of the permanent magnet, and this motion induces eddy current in the aluminum former. Now, the interaction between these eddy currents and the magnetic field produces a opposite torque, and this opposing torque acts as a damping torque which reduces the oscillation and enable a quick settling of the pointer to its final position. Okay. Then the last component is a pointer and scale. Let's break that pointer and scale into two parts. First is pointer and second is scale, and let's discuss about that very quickly. The pointer in the case of PMMC tool is a lightweight and rigid, which ensure minimal inertia and quick response of the device. It is directly attached to the moving coil of the system, so its deflection accurately represents the coil movement. Okay. Most of the time a counterweight is provided to balance the pointer and reduce any gravitational error. Okay. The pointer moves smoothly without oscillation due to effective electromagnetic damping which is provided by the former. Okay. It allows precise reading, especially for small current and small voltage changes. Okay. The scale of PMMC instrument, as I have already mentioned, is linear or uniform because deflection is directly proportional to the current it is measuring. Okay, the linear scale enables easy interpolation or interpretation and high reading accuracy of the device. Okay, the scale is clearly graduated, usually for ammeter in amperes or for voltmeters in volts. Okay, mirror scales are often used to avoid any kind of parallax error. Okay, the scale length can be made large to improve resolution as well as the readability of the device. Okay, so this is the basic construction of a PMMC instrument. Now, once we have understood the construction, now it becomes very easy to derive the torque equation for this kind of instrument. Okay, but before we actually derive, let's see some of the parameters that we are going to use in our equation. So L and D are the length of the vertical and horizontal side of the coil. So if I say this was, say I am not drawing former right now, I am directly coiling it. So in this case, say this was the length, okay, and say this is the magnetic system. Okay, so in this case, this is the L I am talking about. Okay, and this is the D. So this is the L length, and this is the horizontal side of the coil, which is the D. N is the number of turns. B is the flux density in the air gap in Weber per meter square. I is the current which is moving through the moving coil. K is the spring constant of the suspension, and say theta is the final steady state deflection of the moving coil. So now force on each side of the coil, or each side of the coil experience a force very similar to what we have seen in case of galvanometer, which is NBI L into sine alpha, where alpha is the angle between direction of magnetic field and the conductor. In this case also, the field is radial, therefore alpha is 90 degree, and we will always see the force to be equal to NBI into L. Okay, so when you have this force, and the torque can be given simply by the force into distance, and when I say distance, in this case it is so packed system that D is the width of the coil. So this was the width of the coil, and I am calling this. Sometime it is also called the diameter of the coil, but since you can see that it is not circular in nature, it is not appropriate to call this D as a diameter. So better we will call the horizontal length of the coil. Okay, so this torque, deflecting torque TD, is given as force into distance, or the force NBIL into D. Okay, L into D is nothing but the area of the coil. Okay, so I will say that TD is equal to NBA into I. All right, so I am calling again this as first equation. So this is the deflecting torque. Okay, now if you see this very carefully, this NBA all are constant. This was number of turns, this is the flux density. If you are not changing the magnets, the flux density in the air gap will be constant, right? Area is also constant because you are not playing with the number of coil once it is wound on the former. Okay, so all these things are constant. We have also seen this in the case of galvanometer. Okay, and you can replace this with a constant. Say I am calling this G. Okay, to have homogeneity between the galvanometer and this PMMC tool. So deflecting torque can be simply written as TD equal to G into I. I am calling this as equation 2. Fine. Now the spring control provides a restoring torque in this case. Okay, and you have, say in this case, say you have this coil moving. Okay, this is connected with a spring, right? And say there is a twist in this, or there is a movement in this coil, say with at an angle of theta. Okay, right? This will also experience of torque which is proportional to theta. Okay, the spring will also experience a torque which is proportional to theta, and Tc can be given as proportional to theta, or Tc can be given as Tc equal to k into theta, where k is the spring constant, right. For final steady state deflection, this Tc has to be equated with Td, or from the previous equation, say this from second equation, I am calling this a third equation, okay. Second has to be equated with third, okay. So when Tc equal to Td, this Gi is equal to, so this is Gi, Gi equal to k theta, or theta equal to G by k into I, okay. So the current I is equal to k by G into theta, say I am calling this a constant. So this current is again directly proportional to the deflection, and that is why we discussed that the scale of the PMMC tool is linear in nature, okay. So as the deflection is directly proportional to the current passing through the meter, where k and g both are constant, we get a uniform scale for the instrument, okay. Now once we have understood this PMMC construction and the torque equation or the deflection equation, okay, we have to also see that how this PMMC can be utilized for developing ammeter as well as voltmeter, because ultimate aim of this analog tools is to have application in such a measuring or electrical parameter measuring tools, okay. So in the ammeter or even in the voltmeter, there is a clear distinction between the micro devices or micro ammeter or micro voltmeter measuring devices, as well as in the higher order measuring tools, like the tools which can measure in amps or say tens of amps, okay. So in micro ammeter and low range milliammeter, say to a range of 20 milliamp, the entire current to be measured is sent through the moving coil, okay. This is because the instrument springs serve as a current lead itself to the moving coil, okay. Their current carrying capacity limits the current that can be safely carried is about 20 milliamp, okay. For higher current, when you have current, strictly speaking, when it is greater than 20 milliamp, the moving coil is shunted to bypass current around the coil and the spring to safeguard the spring itself, okay. So this shunting methods, we have to see that how it can be shunt to increase its range basically. So till now I was talking about 20 milliamp or so, that order of current, okay. So of course this can be completely passed through the springs, okay, which acts as a current lead that we have also seen, okay. But what if I want to measure more than 20 milliamp, okay, say few order of say few amps or so, okay. So for that kind of thing, the moving coil tool has to be shunted to bypass current around the coil and the spring, okay. So we'll see later in the next lecture that how we can provide this shunt to extend the range of this PMMC tool from say less than 20 milliamp to greater than 20 milliamp, okay. Similarly, if you want to apply or utilize this PMMC tool in voltmeters, they have their own construction constraints and they have their own modifications, okay. So voltmeters on their own have a range of around say 0 to 50 millivolt or 0 to 100 millivolt at max, okay. However, voltmeter having higher range uses a moving coil together with a series resistance, which we call multiplier. We have also came across this multiplier when we were talking about galvanometers, when we have seen that to convert it into different kind of ohm meters, sometime you have to connect these multipliers, okay. So this is a very similar concept, that when voltmeters having higher range has to be defined, okay, you have to utilize a moving coil together with a series resistance, which is known as the multiplier, to limit the instrument current to the desired value, and that's how usually voltmeters are manufactured even from a low range measuring voltmeters based on this PMMC tool. Okay, so most DC voltmeters are designed to produce full scale deflection with a current of the order of say 20, 10, 5 or say 1 milliamp. Normally a value of 1 milliamp is used. Okay, therefore, excluding low range current measuring instrument, most DC ammeter are actually 50 millivolt or say 100 millivolt operated with a suitable shunt. Okay, so while voltmeters are low range milliammeters operated with a suitable series resistance. So we will see in the next class that how we can convert these voltmeters or say ammeters which is existing with this PMMC tool, of course not of the scale of say more than 100 millivolt or say more than 20 milliamp, and how they can be modified using series resistances as well as shunts to convert them high order magnitude measuring tools, be it ammeter or be it voltmeters. Okay, so we will see the strategies to improve their ranges in the next class. Thank you.